The seven-layer AI stack is a revolutionary blueprint for intelligent computing, introducing the OSI model for the AI era. Just as the OSI model revolutionized how we think about networking by providing a clear, layered framework for understanding complex systems, the AI industry has evolved its own fundamental architecture. This seven-layer blueprint represents more than just a technical framework. It's a complete reimagining of how we build scalable, autonomous AI systems from the silicon up to the user interface. From the chips humming in your data center to the co-pilots transforming your daily workflows, every aspect of modern AI can be understood through this elegant, layered structure. This isn't just academic theory, it's the practical blueprint that companies like OpenAI, Google, and Anthropic use to architect systems capable of reasoning, learning, and acting autonomously at unprecedented scale. Layer 1. Physical, the atomic foundation of intelligence. Silicon, memory, power, and cooling. Everything begins with atoms, specifically the silicon atoms arranged in increasingly sophisticated patterns to create the computational substrate for artificial intelligence. This physical layer represents the raw materials from which intelligence emerges. The hardware revolution. GPUs, or graphics processing units, originally designed for rendering video game graphics, have become the workhorses of AI training and inference. ASICs, or application-specific integrated circuits, custom chips like Google's TPUs and Cerebrus's wafer-scale engines designed specifically for AI workloads. Network fabrics, high-speed interconnects, InfiniBand, NVLink that allow thousands of chips to function as a single massive brain. The power and cooling challenge. Training large AI models consumes megawatts of power and generates enormous heat. This layer must solve fundamental physics problems. How to keep thousands of high-performance chips cool while providing stable, clean power. The world's most advanced AI systems require dedicated substations and industrial cooling systems. Memory hierarchies. AI models need to access vast amounts of data quickly. This layer implements sophisticated memory hierarchies from high-bandwidth memory, HBM, directly attached to processors, through multiple levels of cache to massive storage arrays containing training datasets. Layer 2. Link. The nervous system connecting silicon minds. System software stack for massive scale. The link layer is AI's equivalent of a motherboard, but one that spans entire data centers. This layer makes thousands of individual chips function as a coherent, unified computational entity. Scale up versus scale out. Scale up is making individual nodes more powerful through faster chips, more memory, and better interconnects. Scale out is connecting thousands of nodes through sophisticated networking and software coordination. Critical technologies. CUDA and ROCm, low-level programming frameworks that harness GPU computational power. Distributed training frameworks, software that coordinates training across thousands of GPUs. High-performance computing fabrics, ultra-low latency networks that make distant processors feel local. Resource management, sophisticated schedulers that allocate computational resources dynamically. The emergence of AI-specific infrastructure. Traditional data center architectures weren't designed for AI workloads. This layer represents a fundamental rethinking of how we build computational infrastructure, optimizing for the specific patterns of AI training and inference. Layer 3. Neural network, the architectural brain, where model architecture lives. This layer houses the mathematical structures that give AI its intelligence. It's where abstract concepts like attention, transformers, and neural pathways become concrete implementations capable of reasoning and generation. The core architectural innovations. Transformers, the revolutionary attention is all you need architecture that powers modern language models. Mixture of experts. Architectures that activate only relevant parts of massive models, improving efficiency. LRA, or low-rank adaptation, techniques for efficiently fine-tuning models without retraining from scratch. Advanced techniques, RAG, or retrieval augmented generation, combining parametric knowledge with external information retrieval. Speculative decoding, predicting multiple future tokens to accelerate inference. Pruning and distillation, techniques for creating smaller, faster models that retain most of the original's capabilities. The mathematics of intelligence. This layer implements the mathematical operations, matrix multiplications, attention mechanisms, activation functions that somehow give rise to reasoning, creativity, and understanding. It's where silicon begins to think. Layer 4, context, where reasoning comes alive. Memory that isn't RAM. The context layer represents a fundamental departure from traditional computing. Here, memory doesn't mean RAM or storage, it means the model's ability to maintain coherent understanding across long conversations, complex reasoning chains, and multimodal interactions. Key capabilities. Prompting, the art and science of communicating with AI systems through carefully crafted text. Test-time compute, allowing models to think longer on difficult problems, trading computation for better answers. Chain of thought reasoning, breaking complex problems into step-by-step reasoning processes. Multimodal context, integrating text, images, audio, and video into unified understanding. Tokenization, the language of machines. This layer handles the crucial translation between human language and machine-readable tokens. Advanced tokenization schemes enable models to understand context, handle multiple languages, and process various data types seamlessly. Working memory versus long-term memory. Unlike traditional computers, where memory is about storage capacity, AI memory is about maintaining relevant context, understanding relationships, and building coherent responses across extended interactions. Layer 5, agent, where models become actors. LLMs with memory, tools, and external APIs. The agent layer transforms passive language models into active, goal-oriented entities capable of taking actions in the world. This is where AI stops being a sophisticated autocomplete and becomes something approaching autonomous intelligence. Agent capabilities. Persistent memory, maintaining information across sessions and tasks. Tool usage, calling external APIs, running code, accessing databases. Goal-oriented behavior, working towards objectives rather than just responding to prompts. Learning and adaptation, improving performance based on feedback and experience. Swarm intelligence, when multiple agents interact, emergent behaviors arise. Agent swarms can tackle complex problems through collaboration, specialization, and coordination, like a digital ecosystem of intelligent entities working together. The transition from reactive to proactive. Traditional software waits for user input. Agents can initiate actions, monitor environments, and respond to changing conditions autonomously. This represents a fundamental shift in the human-computer relationship. Layer 6, orchestrator, Kubernetes for AI minds. Managing autonomous actors at scale. The orchestrator layer solves the complex challenge of managing, evaluating, and deploying multiple agents across different environments. Think of it as Kubernetes, but instead of managing containers, it's managing intelligent, autonomous entities. Core responsibilities: agent lifecycle management, spawning, monitoring, and terminating agents based on workload demands. Resource allocation, distributing computational resources among competing agents. Performance evaluation, continuously assessing agent effectiveness and safety. Environment management, providing agents with appropriate contexts, tools, and permissions. Deployment orchestration. This layer handles the complex task of deploying AI agents across different environments, from the cloud infrastructure to edge devices, while maintaining consistency, security, and performance. The challenge of autonomous systems. Unlike traditional software that follows predictable code paths, agents can behave in unexpected ways. The orchestrator must provide guardrails, monitoring, and intervention capabilities while allowing agents the autonomy they need to be effective. Layer 7, application, the human interface, where intelligence meets experience. The application layer is what users see and interact with, but it's just the tip of an enormous technological iceberg. This layer translates the sophisticated capabilities of the underlying stack into intuitive, useful experiences. Modern AI applications. Copilots, AI assistants integrated directly into workflows. GitHub Copilot, Microsoft 365 Copilot. Autonomous robots, physical embodiments of the AI stack in manufacturing, logistics, and service industries. Workflow agents, AI systems that automate complex business processes. The interface challenge. Designing interfaces for non-deterministic intelligent systems requires new approaches. Users need to understand what the AI can and cannot do, provide appropriate context, and collaborate effectively with autonomous agents. The revolutionary implications. Why this framework matters. This 7-layer model does more than organize technology. It provides a roadmap for understanding and building the next generation of intelligent systems. Each layer builds upon those below it, creating emergent capabilities that wouldn't be possible with traditional computing architectures. Emergent intelligence. Intelligence isn't located in any single layer. It emerges from the interaction between all 7 levels. The physical layer provides raw computation.